If you need me to, I can plug in, but I think you got my slides. There we go. What's that? No, no, he's got it. Yeah. Well, hi, everybody. My name is Andrew Young. I'm a computer scientist at San Diego National Laboratories in the Scalable System Software Group. So today I'm going to talk about some of our efforts that we're trying to put together in relation to what I'm sort of calling virtualized supercomputing, for lack of a better term, essentially. So I'm going to give a quick little motivating couple of sentences. I'm going to talk about our ideas with high-performance virtual clusters, how containers may fit into some of this. I'm then going to dive in a little bit to an interesting project called Vanguard and how that may be of interest, and we can use this as a vehicle for driving some of the more interesting research that I'm trying to define, and really start to open up the idea. Really not an answer, but start asking the questions about how we work on sort of this convergence, and is this idea of virtualized supercomputing something that is viable? So at Sandia, we have a bunch of emerging use cases for running sort of large-scale machine learning and data analytics workloads. And these are coming up out of the woodwork all the time. So simple idea of using machine learning for sort of ensemble or workflow steering, removing the human in the loop and replacing it with AI in the loop of some sort. There's a lot of possibilities in terms of mesh refinement and how you could essentially, shrink the search space for what you need to do for your mesh generation, for your simulations, adaptive numerical solvers. Maybe we don't have to, again, do an entire search space. And then we certainly have a lot of, in situ analytics use cases for maybe feature detection while your MPI simulation is running, so that we can either steer the application or abandon it entirely or refine the mesh further to further focus on an area of interest, perhaps. So we also have projects like studying reinforcement learning for actually targeting large-scale system behavior, which is a rather interesting thing that we just started. And of course, streaming analytics, this idea of fire hose. There's actually, Sandia has the firehose.sandia.gov benchmark, which really starts to describe some of the streaming analytics. So really, this kind of brings forward the question, how do we support these workloads on DOE's leadership class systems, some of our large and heavy supercomputing investments. And right now, that's certainly an open problem because, as you guys here are all well aware, these run vastly different, software and libraries and really represent different software ecosystems than the traditional MPI use cases in the simulations. So yeah, again, we're sort of at this forefront, or maybe have been for a while now, between supercomputing and sort of emerging analytics. A lot of times what we see, or what sometimes the current solution is really to have two separate machines. We've got our simulations, our big supercomputers for that, and then we have separate data analytics or otherwise clusters. And while this does obviously work today in some fashion, I think there's growing arguments that this is not a sustainable model. And I'm certainly going to sit here and tell you that I don't think it's sustainable. These things end up being inefficient and expensive. You're maintaining completely separate systems. And as these workloads become more coupled together, if we're again going to have machine learning doing application steering or having to look at some of the checkpoint data, for instance, of an MPI-based simulation to do in situ analytics, there's further use cases for doing that on the same machine that your simulations are currently running. So, and to transfer all that data will soon be problematic. So there's really this kind of idea that, boy, it'd be nice if we had a converged system for this. And in that sense, I think there's a lot of research that's been happening from sort of the big data platform services, to try and start to leverage some of the supercomputing aspects. I think Tony talked about some of that already, and those are great. I'm fully behind that. I think there's a lot of optimization that can be done, both on node and inter-node. However, I also think that from a supercomputing system software perspective, we also need to come the other way. So we need to provide additional services and capabilities from an operating system and middleware level to really sort of help with some of that. So do we really actually consider redesigning how we do supercomputing to support the mission needs of both simulation and analytics? And that's an interesting question. So I'm going to make an argument that various, the broad term of virtualization can help that. So with this, we have the design of high-performance virtual clusters. The idea is that we can simply run separate, what we would call or consider clusters today, on supercomputing resources. It's important to note that what we're talking about here is not simply loading a Hadoop cluster on top of a normal, MPI-based cluster. These supercomputers are very different than, at the extreme end from traditional clusters. There's no Ethernet, let alone even InfiniBand. They have specialized node operating systems. If you're lucky, it's a stripped down Linux operating system, sometimes an entirely specialized I/O or OS entirely. Separated I/O libraries, storage is completely different than what you're used to. So it'd be nice if we can figure out how to actually bring in some of these different software ecosystems to this architecture. And obviously, virtualization lends itself to some of this. So we've done some of this. We've basically, I won't go into the details, but we've hacked up a Cray XC series, a testbed that is essentially representative of the Trinity supercomputer at LANL that we share with LANL. And essentially brought in a KVM, a type 2 hypervisor. Doing a lot of special tuning and custom configuration, we can get fairly good, or what we're going to call near native performance, which is a little hand wavy, but bear with us. And that we can actually run some Apache Spark workloads on a small XC supercomputer, and get fairly good performance. This is something that we couldn't even do natively using a Cray. So. But of course, what about containers, right? It's all the buzz. Ooh, this is actually working great. Next slide. I jinxed it. There we go. So everybody talks about containers, and there's a lot of questions about how these are going to apply to high-performance computing. So I'm going to quickly just try and define things that we actually care about in the HPC world when it comes to containers. We want to enable this idea that people can bring their own environment, right? That's great. That's really powerful. And that enables data analytics and machine learning workloads just to stroll on in with their already predefined software stacks and plop them on our supercomputing resources. We like the idea that these things are composable and that they're documented. It's easy to look at a Docker file, for instance, and know how this image is built and then reproduce that. The idea of portability is really attractive, as well as direct integration with things like Git, or GitLab and GitHub. So what we don't want from some of the container features, and again, I'm referring kind of vaguely to the idea of Docker here, is we don't want overhead. HPC is not, overhead's very expensive, and it's something that we'd like to avoid at all costs. We don't care about running microservices. What I'm talking about are entirely separate instantiated environments, not running your MySQL server on a Cray. Maybe there's justification for it, but that's not our first priority. We're not really too worried about unknown provisioning. I don't think C groups is really going to be useful with that. I think this is where sort of this merger between virtualization and containers really starts coming into play. And we certainly don't want to give root access to anybody on these systems, which is something that even simulated root access, even if it's namespace, that's potentially dangerous, especially when you start integrating with separate file systems, like a Lustre backend. And there's a lot of commodity networking stuff that just isn't applicable. So we're sort of working on this, container vision at Sandia, and the idea is that we'd like to enable our integrated code teams who do all this heavy development to start and do their development on their laptops and be able to move this in some capacity to a supercomputing resource, or a CTS cluster, or potentially, Amazon EC2. So, boy, that'd be really nice, right? And developers are really starting to turn around on this. And if we can show that these HPC groups can use them, these large integrated code teams that are spend a lot of time on, math kernel library optimizations, that this is useful and efficient for them, then that's going to make everybody else's life easier who wants to bring in a non-standard software stack. So, and we also want to worry about how we deal with multiple architectures and compilers. So a lot of the code teams need to run not only on the K&L systems as part of Trinity. As soon as Sierra is fully up in production at Livermore, those codes need to run there as well. Totally, completely different architectures. And I'm going to talk a little bit about a third architecture that these codes are going to have to worry about. And again, performance matters. So whatever we do has to be performant. So this sort of idea here, we can kind of encapsulate where you would start with a laptop, build a container in Docker, which we're allowing our code teams to do today, leverage internal GitLab registry services. We don't want to push this to GitHub because some of these are not public codes. So we can have a container registry service. And then package this however we need to. And in this case, we're looking at Singularity in particular for how this fits in. And I think it's a best fit. So we did some experiments, and this is the idea where I'm going to tell you a tale of two systems. And basically, again, we hacked up a cray because that's what we do at Sandia. And we allowed Singularity to run on a cray, and we also ran some Docker containers on MSI EC2. We tried to, well, again, these aren't identical hardwares. We tried to keep them as close as we could, matching at least the Ivy Bridge CPU type and the best possible networking that we could get from Amazon EC2, and really trying to figure out, all right, how well would these workloads work? And you know, we see that Singularity actually provides pretty good performance. So here's my KVM work running just a HPCG, so conjugate gradient. This is sort of the bookend benchmark that we use that is typically more representative of our actual mission applications. So we basically hacked up Cray, and the important thing here is we removed the standard MPitch or Intel MPI that we were using and replaced it with a Cray optimized MPI library, which has support for the Aries interconnect that we care about. And when we do that, we get native performance. This 90, that 0.2% is really just the simple fact that we're dynamically linking versus statically linking our application. That's not an issue of Singularity or containers. That's an issue of not statically linking. So, and this looks better, a lot better than some of the stuff when we run on, Amazon EC2. We see it a couple nodes, it looks good, and actually those nodes are a little fatter, but performance quickly drops substantially just due to the network, which I'll show you. And that's actually not too surprising, but this is, I would say HPCG is one of the friendlier benchmarks that we have towards interconnect performance. So when we actually start to look at it from just using an all reduce. So looking at 8-byte alt reduce, which is something of heavy interest to Sandia and some of the apps there, we see that there's 2 orders of magnitude difference in this just between EC2 and the Cray. So again, this is really just to show that there's a lot of optimization that can happen and that is available on some of these supercomputing resources. And boy, it'd be nice to support different ecosystems that can use this sort of performance. So, all right, I've talked about VMs, I've talked about containers. Do they blend? And I'm gonna make the argument that yes, I think they do. And we're working on trying to blend them. So I think the idea of virtual machines allows us to abstract some of the hardware, remove that complexity of the supercomputing infrastructure from developers, while still using containers on top to allow users to bring in exactly the environment that they define that they need. And our code teams, the heavy simulation code teams like this, and of course that provides a nice open door for bringing in different non-standard, non-MPI based workloads into these systems too. But we're tip of the iceberg here. I don't mean to say that it's all done by any means, it's not. There's still a huge problem of resource management and scheduling. There's a huge issue of how do we deal with some of the extreme heterogeneity that we're about to see and sort of this end of Dennard scaling and this post-Moore era, for lack of a better term. And really, is there anything that we can do from a computer architecture, from a supercomputing architecture standpoint to aid this further? And this is something that we're actually looking at through this new project called Vanguard. So the idea here with Vanguard is that it's not a test bed, but it's not a full ATS, CTS platform. ATS being the large scale NNSA, ASC deployments. So Trinity at Lanel and Livermore with their new Sierra machine, the new IBM machine. And so they're very expensive machines. There's a lot of investment that needs to happen. And really what we'd like to see is an easier way to evaluate and determine whether or not new hardware technologies are viable for our mission codes. We'd like to increase the technology choices. I don't want to be bound to just what one vendor tells me they can provide and that's it. It'd be nice to encourage a more diverse ecosystem. So that's what we're trying to do with this Vanguard project. So phase one of that is actually going to be called Astra. I can now tell you that. I can't tell you any of the details other than it will be a petascale ARM system. So hopefully in a couple of weeks, there'll be a little more info on that. But again, this is going to be of a significant scale, but not an exascale yet. The idea is let's prove out the ARM ecosystem. Let's figure out if there's something that we can do here. There we go. And really make sure that this sort of new and emerging CPU architecture is actually something that can be useful for our integrated code teams. And that requires a lot of heavy lifting on our part. There's a lot of math libraries, compilers that need to be optimized. There's a whole lot of extra work that needs to be done to prove out our codes will work and scale. However, that also gives us a really wonderful opportunity, which I'm trying really hard to take advantage of, and that is we get a chance to sort of play around with the software stack and redefine it to some degree. So we're bringing in new programming environments. You know, we have the opportunities to really do some experimentation from an OS and middleware standpoint. And again, these are specific plans for this, and we are literally planning to demonstrate containers and VMs and supporting these non-standard machine learning and data analytics workloads using this prototype. So our first priority is making sure that, you know, in determining whether or not ARM is a viable platform for our large simulations. But beyond that, because we're putting in this effort, that gives us an open door to explore some of these more emerging workloads, which is really interesting. So, pointing the wrong way. So we're trying to devise a new software stack. So we have the ATSI software stack that's going to be some combination of a vendor operating system, the TriLab operating system stack, or potentially borrowing directly from open source projects. We'd like to have a kind of converged and agreed upon software environment so that developers know exactly what they're getting, and we get to define some of that. That may be based off of the open source efforts such as OpenHPC, for instance, but because we're leveraging VMs and containers, we can bring in some more interesting things. So to really try and wrap this up, because I think I'm totally out of time, sorry. You know, I think these convergence efforts are promising, but this is really only the start. We need to do a whole lot more. And we can leverage, I'm making the argument that we can start to leverage some of these interesting prototype architectures to start to change, you know, the fundamental way in which we use these supercomputing resources away from just a batch model into something potentially more interesting. And there's a lot of system software work that we need to do, but it's fun, it's interesting, and I think if we get it right, we can actually support a whole lot more of our workloads that we will see in 5-10 years down the road and be able to leverage the massive investments that the DOE makes in supercomputing. So I think that's it, yeah. So thanks.
So why do you have VMs and containers?
Yeah, yep.
What happens if you just use containers?
Containers, again, allow you to bring your own environment to some degree. However, they don't give you full resource management control. So if I wanted to run my own job schedule like Yarn, I need that extra level of separation to do that. I want to start to, with high performance, you know, virtual clusters, I want to basically do block allocations where I can say, you know, my HPC scheduler, please get out of my way. I'm allocating these resources for a streaming analytics that can move up and back. And it's very easy to do that with VMs. I can pause, I can move resources, I can, you know, abstract some of the details of the individual hardware. But the cost of virtualization is decreased substantially, and there's no reason that we can't potentially do that. So, and then with containers, it's really just a nice feature to bring in our own environment. So
What's your mapping of containers to VMs? One?
we're working on that. That's an open research question. How's that? That's essentially the topic. What I don't want to do. Essentially, yes. The question is, how does that then map to an individual node architecture? And as we see with some of the new, again, the Power 9 systems with Sierra, or sorry, Summit, right? They're the identical system minus GPUs, right? Minus, I think, 2. Either way, those are very, very large nodes. And there's a lot of times our simulations may not be able to use all those resources at any one time. We may be hitting the GPUs, for instance, and there's a lot of available Power 9 cores that it'd be really nice to utilize. So then you have the idea of, all right, can we bring in a separate VM and do resource isolation intra-node, and then from there layer a container system on top of it. So we're starting to play around with things like that and wrangle with big big individual node architectures. So how that divide happens and to what degree, I think it's still very much open and up in the air, and will only get more complicated as we look towards future architectures. So
if you chop up nodes, once you have lots of classic cloud overheads, things like that.
Potentially, right? Yes, we have to be very careful about this. That being said, I don't think what we don't want to do is allow the operating system to do that, because the operating system will do a worse job than what we will do. We've got some data that shows this, but for instance, there's this argument that containers don't always contain, right? Linux C groups can sort of walk all over other processes if you're not careful. So the idea with VMs is using it as more of a brute force sort of allocation of individual resources. So I'm going to allocate this many CPUs and then pin them appropriately. So I'm less worried about running 100 containers on a Power 9, node. I'm more interested in 2, where one is, an analytics job that's coupled to my simulation, for instance. So.
San Diego supercomputing centers, they're running Singularity.
Yep.
They're doing it on bare metal.
Yep.
You guys talk to them?
Yeah, absolutely. Yep. And we're running it on the Cray as bare metal too. So we actually work with the Singularity group a lot and are trying to get some new features pushed in. I don't think I probably can't speak too much on that, but I think Singularity is a really interesting technology, and it works. It's containers that actually work for HPC. Unlike Docker, where Docker is a great technology that's applicable to sort of the data center world. So we can take some of those features, but not the ones that'll hinder us in other ways from precluding performance, for instance. So yes, there's many people that are active in this. We are not unique in this. So and there's a lot of hard lessons to be learned.
The reason I brought it up is the people in San Diego, since they're running bare metal, have they encountered problems with doing that said, gosh, I wish we had virtualization?
I don't know. That's a good question. That's probably a worthwhile conversation to have. Again, if you want to look at bringing in, say, like, your resource manager with Yarn, for instance, you're going to have to today work with the batch scheduler. Or what if I want to support like a Kafka streaming analytics job? How do I make that work with my batch scheduler? So not every job is batch, and the HPC community has been set up for a very long time to deal with just batch. So there's some limitations there, I think, that are that may not be the answer. Again, this is exactly the conversation and the debate I want to have. I don't have an answer, but I think we need to start asking ourselves: can we improve Slurm? Is there another technology? Is there another scheduling? Yep. Well, and then you got batch support now in Kubernetes. Why don't we just run Kubernetes and do our batch jobs that way?
I have a question. I don't quite understand why HPC avoids these technologies that appear to do exactly what they want.
Yeah, I agree. I don't think that being said, I think the capabilities of Kubernetes and their batch mode is is not nearly what you can do with, say, Slurm today. But that's not, I was going to say that that's something that can change in a couple of years with some development efforts. So, but yeah, where is that right separation? How do we support more than just batch on these systems? And it's a resource management and allocation problem, and a fun one. So.
Okay, great.
Cool.
So let's thank Andrew for talking.
Thanks.